Good morning. My name is ILMA HUSSAIN and my roll number is 225040 and my topic for presentation is Rolle's theorem. So the Rolle's theorem states that if a function fx defined in a closed interval a comma b satisfies the three conditions that are: first, fx is continuous in closed interval a comma b, fx is differentiable over open interval a comma b, and lastly fa equals to fb, then there exists at least one point c such that small a less than c and small b is greater than c, at which f dash c equals to 0. Now for proof, we have a graph, and in that graph we have a curve having 3 points a, b and c that are having x coordinate of a, x equals to a, x coordinate of b, x equals to b, and x coordinate of c is x equals to c. And we also know that y equals to fx is a function, then y1 equals to fa and y2 equals to fb. As given in the theorem above, fa equals to fb. Therefore, y1 equals to y2. Coordinate of point A is x comma y1. So we substitute value. Therefore, coordinate becomes small a comma fa. Similarly, the coordinates for point B are small b comma fb, and coordinate of point C are small c comma fc. And as PQ parallel to x-axis, therefore theta equals to 0, then tan theta equals to 0, and it is also the slope, so it is equals to m. And as it is a slope of point PQ, m equals to 0, then dy by dx is also slope, which is equals to f dash x, and therefore equals to 0. Therefore y equals to fx at point C, then y equals to fc. Therefore dy by dx equals to f dash c equals to 0. Now since fa equals to fb, where x takes value greater than the function fx should either increase or decrease unless fx is constant, and in this case theorem is at once established. Now let us move towards the graph for a better understanding. Now we can say that if we are having a point C here, and when we move from point A towards C, the graph tends to increase, as we can see here. But if we move from point C towards point B and thereafter, the graph tends to decrease if we take value of x greater than f. Now we take a case of point C, where we move from point C to B and afterwards. Suppose the function increases. When x takes a value greater than a, then function should increase. So when the function starts moving from A, it tends to increase till point C. Till point C, and when we move towards B from C, it tends to decrease afterwards. So if we start from point A in figure, where fx again takes value fb equals to fa and fb equals to fc, in which y coordinates are same, a and b are equal, having the same value, therefore fa equals to fb. Now it must cease to increase at some point C, where x equals to c, such that a less than c and b greater than c, and begin to decrease afterwards. So here we can conclude that the curve increases from point A to the desired point C, and from C to B it decreases. Here suppose we have a point C. If we move from point C with a small value of x and we will mark it as point C2, and if we move towards this side and with a small value of h, we will mark it as point C1. At point x equals to c, there is a maximum value of function, and so fc plus h minus fc and fc minus h minus fc will be smaller than fc, and hence both will have negative value, h being small and positive. H being small and positive means h greater than 0. And we also know that if we reduce smaller number from larger number, we get negative value. So fc plus h minus fc gives us negative value, that is less than 0. And similarly, fc minus h minus fc, already discussed, is also less than fc. So reducing a smaller value from greater value again gives us negative value, that is less than 0. Now we have to define differentiability of the function as it is a condition in the theorem. So right hand derivative of the function limit h tends to 0 fc plus h minus fc upon h less than 0. This is already negative, so it will give a negative value. So right hand derivative of the function becomes negative. Now we will find left hand derivative. For left hand derivative, we take limit h tends to 0 fc minus h minus fc upon minus h, as we are taking negative limit. So this value was negative. Here we can see this value was negative, and so the negative sign of this value cancel out the negative sign of minus h, giving us a positive value. So left hand limit of a function is positive. And now right hand limit of the function is not equal to left hand limit of the function. It is the case when they are having different limits. So here we can conclude that as h tends to 0, the above expression tend to negative and positive respectively, unless each of them is 0. If they have different limits, right hand limit of the function is not equal to left hand limit of the function, that is f dash c does not exist, which is against the hypothesis. Hence each of the above limit must be 0, f dash c equals to 0, where a less than c and b greater than c. Now let us discuss a question based on Rolle's theorem. So the question is, verify Rolle's theorem for the function fx equals to x square in closed interval. We have to note that we have been giving closed interval minus 1 to 1. So now let us see the solution. So fx equals to x square in minus 1 to 1 as we are given in the question. So we'll put limits, we'll put values. F of minus 1 is minus 1 ka whole square is equals to 1, and for this f1 equals to 1 ka square equals to 1, and f dash x equals to 2x. We will differentiate it, so it will come 2x. And now at c it is f dash c, so we'll substitute c, so it will become 2c. Now according to the theorem, f dash c equals to 0. Then 2c equals to 0. Then we will find the value of c from here. C equals to 0 by 2, which will come 0 is equals to 0. As 0 belongs to closed interval minus 1 to 1, therefore minus 1 less than 0 and 1 greater than 0. So the value of c comes to be 0, and hence the Rolle's theorem is verified. Thank you.